Hello everyone, welcome back. Today we will be discussing about HEMU transmit packet power analysis for different MCS combination and RU size. So the learning objective in this experiment is to create a multi-user high efficiency format configuration object for 11AX multi-user waveform with 9 equally sized RU of size 26 tones. So initially I'll set RU allocation index as 0 for multi-user waveform configuration. Then configure the TJX channel for 20 megahertz bandwidth using WLAN TJX channel system object and vary the modulation and coding scheme from 0 to 9. So MCS support in 20 megahertz bandwidth is from MCS 0 to MCS 9. Then record the transmit power for different MCS combination and see whether the transmit power is fixed or is it changing with MCS. Then the transmit power computation is done both in time domain as well as in frequency domain using a system object called spectrum analyzer. And lastly, we vary the allocation index and analyze the transmit power for different MCS and RU size and also see the frequency domain waveform using spectrum analyzer. So I have discussed about this RU allocation index maybe in the previous experiments as well. So if you initialize the HEMU transmission using WLAN HEMU configuration object, the input argument is RU allocation index. I had shown the tables also earlier. Even MathWorks website has the reference where you can read more on RU allocation indices. So I have considered 3 examples that are 0, 15, and 96. If you set it as 0, then the entire 20 megahertz bandwidth is divided into 9 equally sized RUs of 26 tones, and this is the minimum RU size possible in 11AX. And the 9 users are occupied here. So this is given by RU numbers. RU numbers and RU indices are same. And if you say change this RU allocation index from 0 to 15, the 20 megahertz bandwidth is then divided into 5 RUs, wherein 5 users are occupied or allotted. And first RU size will be 52, second RU size is 52, the middle one is 26 tone RU, then 52, 52. If the RU allocation index is changed to 96, then the entire 20 megahertz bandwidth is divided into 2 resource units, each of 106 tones RU. So this diagram shows RU allocation. This is for the first case where the RU allocation index is 0. This is for the second case where the RU allocation index was 15. Yes, 15. And this is for the third case where RU allocation index is 96. So you can see here there are 9 users, each with equally sized RU consisting of 26 tones. So index 1, user 1 up to user 9. So here middle one, so user 1, user 2, user 4 and user 5 each are of 52 tones. The green color here is user 3 occupying 26 tones, central 13 tones on either side of the central carrier frequency. So here there are only 2 users each of 106 tones and the middle portion of the bandwidth is unused. So this is the baseband TJX waveform. Here different colors indicates the transmit waveform which is plotted for different MCS. So lower order MCS generally takes large number of samples or occupies more time. So the difference between these two plots are x-axis here is a sample index, but here it is a time in seconds. So the blue thing is starting from 0 and occupying almost 5.5 milliseconds, or I can tell it has almost 11,000 samples in it. And this orange or this color is actually starting from 0. Since the colors are overlapping, it is not clear. Maybe when we'll execute the code and understand better. Here what I want to tell is as MCS increase, the time duration required for the transmission of that packet decreases. And this experiment is more about learning from the simulation results. So I don't have anything to tell in slides more. So let's begin the explanation, execute the simulation, and then learn through the simulation results. So coming back to the script. So this is a simple script. Here what we wanted to analyze was we wanted to know, do the power packet, or the packet power analysis for HEMU transmission waveform for different MCS. The main objective was we wanted to see whether the TX power is changing with the different MCS combination. How is the power distributed, or what is the power spectral density across the bandwidth. So this was the main objective. So I scripted a simple program and making use of spectrum analyzer from the DSP spectrum analyzer system object, and trying to sketch this, getting this frequency domain, trying to sketch the frequency domain signal of the multi-user transmit waveform. So code is quite simple. So initially, we initialize this WLAN HEMU configuration object. As I told, RU allocation index is set to 0. Here the number of users are 9, number of R users 9, equally sized each of 26 tones. Then this command shows allocation, meaning this gets executed whenever we write show the allocation. Allocation info will display, like give more details about the RU allocation information, telling like how many number of indices, what is the size of each RU, how many numbers of users are there per RU, etc. Then for the user one, I am setting the payload length as 500 bytes. For the rest of the users, so num length of this gives the number of users. So here, because I have set RU allocation index as 0, this the value of this would be 9. So for the remaining users, for second user to ninth users, I am setting highest MCS and giving the payload size as 1. This I'm doing because I don't want, because I'm changing only the parameters of the first users. I do not want the other users parameters to affect my multi-user TX waveform. So I'm giving the highest MCS, so that each of so that this occupies less TX time, and also the payload size is also set to 1, or you can make it 0. Then the power, these are the arrays which I am initializing. So the power vector is set to a null, I mean initialized to null, MCS, TX length, this and all I'm going to compute inside this for loop. So I've set num packets equal to 10 for, so I'm running this loop 10 times. Every time I'm setting the MCS of first user varying from 0 to 9. So MCS support in 20 megahertz is 0 to 9. So first loop, the MCS for the first user will be 0. Second time, MCS for the first user will be 1. So this actually this MCS varies from 0 to 9. Then I'm storing this MCS in a variable called MCS, and I'm appending it and storing this in capital MCS variable. So I'm getting the PSDU length. Then for all the users, I'm creating TX PSDU, generating the random PSDU for all I varying from 1 to 9 for all the users by generating the random bit, and PSDU length I am taking from this APEP length. Then I'm generating a multi-user waveform, creating a multi-user waveform, and this TX waveform changes every time as MCS change. This you can note, like the number of samples is going to change as MCS changes. Then the number of samples is stored in the variable called sample length, and I am also collecting this in order to display at the end after simulating. I just want to display what is the length of the TX MU wave for MCS varying from 0 to 9. So that I am here displaying here. So this MCS vector will have MCS changing from 0 to 9. TX length corresponds to the number of samples in the TX MU wave, number of complex samples. That is actually complex time domain samples after performing IFFT. Then this figure, I'm plotting the TXMU wave. X-axis is just a sample index. And but here, the second plot, I'm plotting versus time. I'm plotting the absolute value of TXMU wave, but the x-axis is time. So in order to get the time vector, the length of the TXMU wave must be 1:2 length of the TXMU wave must be divided by sample rate. So I plot time versus the I'm plotting the TXMU wave, taking x-axis as a time. So I'm plotting the baseband IEEE 892.11ax multi-user waveform. Then there are different ways of computing TX power. This would have learned in your signal systems or signal processing. So I'm just trying to use all those methods and checking whether all are giving me the same answer. So if you have a discrete samples or a discrete signal, so how do you compare the power associated with it? So if Xi is a complex signal, say it has capital N samples, then the power can be obtained as absolute value of Xi squared, summation high, varying from 1 to n, and divided by capital N. So the same formula I've used, sample length gives a number of samples. So this is one way to compute the power. So this is just compute the variance of the TXMU wave. That is also gives a power. One more method is mean of TXMU wave multiplied by conjugate TXMU wave. So this also must give same power. I mean, say all these three are same theoretically. So again, I'm collecting this power values, TX power values in a vector called power vector. And I'm storing it in average power of TX waveform variable for display. So this average power of TX waveform is for the complete the bandwidth, right? But it is having a value or storing a value for different MCS combination. So now what I do, I compute the average power per subcarrier has power 1 by 256. So power 1 or power 2 or TX power all mean the same. So I take power 1 divided by 256. This is the average power per subcarrier. Then the average power per RU of 26 tones is simply multiply by the average power per subcarrier into 26. This should give the average power for 26 tone RU. If you want to get average power of RU of 52 tones, then it should be average power per subcarrier into 52 should give the average power across an RU of 52 tones. So all these 26 tones, what is the power level across 26 tone RU, 52 RU, I'm just collecting and storing it in a variable so that I display at the end for all MCS combination. So here what I do, I obtain the power spectral density estimate via periodogram method. I'm sending TXMU wave as the input signal. Centered, what it does is it displays uh, the periodogram or the power spectral sensitivity, which is double-sided and which is centered around 0. Then PXX is a PST estimate, that is output variable, output PSD estimate of the signal, and F is a frequency range. Then I make use of one more function called band power, which takes or which computes the average power via rectangular approximation of integral of PSD estimate given the vector Pxx over the frequency specified in F. So you can read more about these function which is available periodogram. If you can see, it computes the power spectral estimate via the periodogram method. So X1 is the input signal, and band power, what it does, it computes the average power using the integral of PST. So PST is given as an input. So it approximates, it uses a rectangular approximation of the integral of PST estimate, and over the defined frequencies F, it is going to compute the average power P, and it's going to return average power P. So that is stored in the average power periodogram. So this is the average power which is computed using the periodogram and band power, that is basically from the frequency domain. So ideally speaking or theoretically, this average power computed should be also equal to the power which is computed in time domain, right? Like using Parseval's theorem. So all these power 1, power 2, TX power, and the average power periodogram must be same for all MCS. So at the end, I'm plotting the average power. At the end, I'm displaying the MCS, the average power of the TX waveform or the complete bandwidth, that is 20 megahertz bandwidth. And what is the average power for 26 tone RU, and what is the average power or 52 tone RU. And finally, I'm doing the frequency domain plot of the multi-user TX waveform. So here I make use of DSP.spectrum analyzer. Sample rate, I set it as SR. SR that I would have computed using this HUMU config. Yes, WLAN sample rate CFG HUM config. So that SR itself, I am giving it as a spectrum analyzer sample rate. So since I want the power density, I'm initializing the property spectrum type as power density. So the averaging method used is exponential. So I'm labeling it as PST, giving the Y limits and giving the title. So I want to see how the TXMU wave looks like in frequency domain, or to be specific, I'm obtaining the power spectral density for TXMU wave. So when I run this code, one thing to note, I'm running this within a for loop for MCS varying from num equal to 1 to num packet, but basically I'm changing the MCS from 0 to 9. Every time I'm computing what is the power, and I'm plotting these two figures, and I'm computing the power using time domain method, and I'm computing the power using frequency domain. So this happens for every MCS. But at the end, only one plot appears when MCS is 9. The PST plot appears only once. So let me run this code. On the fly, like whenever the code runs, you can see how the TX waveform is getting changed for different MCS. So this is for MCS 0, 1, 2, 3, 4, like this, if you had noticed. So the blue thing, the lower MCS occupied largest time, and this is appearing for MCS equal to 9. So here what I want to tell us, this blue curve appeared first from 0 to this, then this curve, then this, then this. So this is for MCS 0, this is for MCS 1, this is for MCS 2, this is for MCS 3, MCS 4. What you can notice is as the MCS increases, the time required for the transmission of MCS decreases. This we have witnessed even in earlier experiments, but I think haven't shown the waveforms like this. Initializing HEMU configuration object, I haven't displayed the HEMU waveform this way. So again, we are emphasizing on the fact that in WLAN toolbox, as MCS increases, the time duration required for the transmission of that particular waveform decreases. So these are the plots here, because I have set RU allocation index as 0. You can see there are 9 RUs being displayed, and with user 9. So if you click on anything, it will simply show, okay, this is RU size 6, 26, RU size is 26, index is 6, user is 6. This gets displayed only once, because this I have obtained, or show configuration I have written, show allocation I have written outside the for loop. These two codes gets executed for every for loop, executed for every for loop. So the blue curve comes for MCS 0, this is for MCS 1, MCS 2, and up to MCS 9. The change is here for this plot, the x-axis is sample index, and for this plot, the x-axis is time. Otherwise, the waveform remains same. Then this is the spectrum analyzer. So I have done the some report. This was done long back, so I'm just trying to explain this from the report itself in order to get some insights. So what I have done is here I have set bandwidth as 20 megahertz, packet size is 500 bytes. So I've changed RU allocation index from 0 to 15 to 96. What I have run just now, it is for 0. You can simply change the RU allocation index 15 to 96 and do the observation. So the observations are already there. You can just verify whatever is present in this report. For example, for configuration RU allocation index 0, this report tells MCS 0 has almost 10, 90, 40. That is 1 lakh 9,040 samples. So let's verify that. Yeah, for MCS 0, it has 1 lakh 9,040 samples. Then as MCS increases, the number of samples gets decreases. And for MCS 9, you have 10,160 samples. Yes, MCS 9 has 10,160 samples. So as the MCS increase, the number of samples transmitted in a multi-user waveform decreases, and also the time duration also decreases. That is why in this plot, like we can see the decreased samples as MCS increase and decreased time duration are required for the transmission of a particular packet. So then what I have computed is the power. So here power used using the time domain samples, that is 1 over n summation I varying from 1 to 10 1 to n magnitude of xi squared. So I told there are 3 different formulas I have used. Let me verify whether all of them are giving the same results. So this is RO allocation information display. For MCS 0, there's the number of samples. The power one, which is computed using the direct formula for TX waveform in time domain. This is computed using the variance. If you go and check here, so the power 1 is using the TXMU wave. Power 2 is using variance. TX power is using again TXMU wave, but using its conjugate. So power 1, power 2, and TX power has to be same. Power 1, power 2, Tx power is same. This is computed using the frequency domain, the average power periodogram. I have made use of periodogram and the band power uh, by from power spectral density. The average power is computed and it is stored in average power periodogram. Average power periodogram. So purposely I have removed semicolon here so that whatever the values I want to get it displayed and the command window gets displayed. So here if you see the average power periodogram is also giving. So using Parseval's theorem, I can tell the power computed in time domain has to be equal to the power computed using the frequency domain representation of the signal. So for MCS1, the number of samples is reduced 55,600. Again, power 1, power 2, TX power and average power periodogram will be same. So this is verified for all different MCS. So MCS0 to MCS9, you can check and all that gives the same answer. Okay, for MCS9, you have 0 to 9, the number of samples is getting decreased. This is the power which is computed using time domain, and this is the power computed using the frequency domain signal, frequency domain representation of the signal. So the last table here gives the MCS, the average power of the TX waveform, that is across 20 megahertz bandwidth, the average power over 26 tones, then the average power computed over 52 tones. So this is for different MCS. This is the power across 20 megahertz. This is power over 26 tones, power over 52 tones. So when we saw this, we were getting the power across 20 tones was 0.1 watts, which is roughly 1/10 of the total power. And this is quite logical because RU size equal to 26 tones roughly occupies 2 megahertz bandwidth. So the entire bandwidth is 20 megahertz, which transmits roughly 1 watts of power, total power. The 26 tone RU is almost 1/10 of 20 megahertz, that is 2 megahertz. So the power spectral density being flat, the power across 26 tone RU is 0.1 watts. For 52 tones, it will be double. So it is 0.2 watts. So you can see for irrespective of MCS, the power across 20 megahertz is roughly 1 watts. For 26 tones, it is 0.1 watts. And for 52 tones, you can see it's nearly 0.2 watts. So that thing we were trying to analyze using this. Yeah, this is a power what we have got, right, using this TX power and band power and periodogram for the complete 20 megahertz bandwidth. So manually we are trying to understand and verify the same. So manual computation is like the last plot was, yeah, the power spectral density. This is across 26, is across 20 megahertz bandwidth. This is computed for MCS equal to 9. Only once I have computed, because for other MCS also it is same. So this is roughly around minus 43 dBm. This is varying. So this is power spectral density. Unit is dBm per hertz. It is not simply dBm, it is dBm per hertz. So if you want the power over some range of frequencies or the bandwidth, you need to multiply this power. First best thing is to convert this power into watts, then multiply by bandwidth. You will give that, you will get the power. So this is you can see there is a dip here around the central frequency. So this is the power across 20 megahertz bandwidth. There are some tools available. For example, go for measurements and do channel measurements. Here you can see what is the power occupied, or you can get the power from the PST. So here, let me take span as 19 megahertz. The central frequency is minus 8.5 exponential 6. Yeah, this occupies almost complete bandwidth. So here you can see it is channel power is 29.931 dBm, or since I have ignored these parts. So consider this the channel power, I can tell it is nearly equal to 30 dBm over complete bandwidth, that is equal to 1 watt. So same fact, whatever I computed, whatever I got it from TX waveform and the power periodogram, I can get through here also. Wherever you want to know what is the power, you can change the center frequency and the span and get what is the power. So the complete bandwidth, the power is nearly equal to 1 watts. So this is being shown here. And the manual computation for the power is same thing. The same thing I have coded there. So here, what is done? So the power spectral density was around minus 43 dBm per hertz, right? This is somewhere around minus 43 dBm per hertz. So what is done is, yeah. So average TX power over RU1 of 26 tones. So if you see here, 26 tones is nearly equal to 2 megahertz of bandwidth. 26 tones is nearly equal to 2 megahertz bandwidth. So here minus 43 dBm per hertz has to be multiplied by 2 megahertz in order to get the average power. So minus 43 dBm is converted into watts, which is 5 exponential minus watts per hertz. This is power spectral density. So this is multiplied by 2 megahertz, then you will get 0.1 watt. So this is the power over 26 tones. If you want to get the power over 52 tones, the 52 tones is nearly equal to 4 megahertz. So this multiplied by 2 gives 0.2 tones. Again, 106 tone is roughly equal to 8 megahertz. So multiplied by 2 gives 0.4 watts. So I have verified this, right? You can change the RU allocation index and verify the column 2 and column 3. That is what happens when you have our allocation index as 16 and then, sorry, 15, and our allocation index as 96. You can just see the same here already the plots. So for example, okay, let me run the code for second case. So the first case here, it displayed the RU allocation. I'm just closing this. Here, this is the TX waveform for different MCS. X-axis is sample index. Here it is the time is the x-axis. This is the power spectral density, right? So let me change. I'll do this case 2. Case 3 you can verify. I'll change this to 15. So in 15, the number of RUs is 5, right? So if it is 15, number of RUs is 5, which is 52, 52, central 26 tone. Then again 52 tones, 52 tones. So now you see a 0, 1, 2, 3. So these are all appearing later, the different colors. Okay, going back to the command window. So number of RU allocation tone as 15, RU allocation index is 15. The number of RUs is 5. RU size is 52, 52. Central one is 26. There are 5 RUs and 5 users. So same thing. So now if you see, the number of samples is reduced for this. So earlier it was beyond 1 lakh, right? So now the number of samples is 55 to 80. 55 to 80. And this power which is computed in time domain has to be same, and it has to match with the power which is obtained from the frequency representation of the signal. And again, as MCS increase, the number of samples decreases. So coming back to the last loop where MCS was 9. Yeah. So the last sample for MCS 9, it is 5680 samples. It is 5680 samples. And this is 5680 sample, right? Sorry, sample index. For first, I think it is 55280. So let me go for sample index. Yeah, 55280. It is 5.5, 10 power 4. So this is for MCS 0. Then 2.84, 10 power 4. This is for MCS 1. Likewise, if you go for last thing, it is 0.568 into 10 power 4. That is for MCS 0. This yellow thing, this corresponds to MCS 9. So again, same observation, as MCS is increasing, the number of samples is decreasing, but the number of samples for any particular MCS is decreased when you compare this column with this column. And this plot is with x-axis as a time, and this is the PSD plot, right? And here also you can check, go for measurements and check the channel measurements and see what is the power occupied in the 20 megahertz bandwidth. So the complete report is here. Similar observation is made. Again, in this case, again, the time, the power associated with the multi-user TX waveform is 1 watt or 20 megahertz bandwidth. But when you go for 26 tones, which is roughly 1/10 of 20 megahertz, you have 0.1 watts power. If you go for 52 tones RU, it is 0.2 watts power, double of this. If you go for 106 tones, it is double of this, it is 0.4 watts power. So this is one thing. And if you see the complete power occupied, it will be roughly around 30 dBm, and it is 1 watts for the complete bandwidth. So this is what was this is what I have to say in this particular experiment. We just wanted to see how the power is varying with what is the power level of different MCS. So conclusion is with the MCS change, the power is not changing, right? But when the RU size is changing, yes, obviously the power will change because the number of tones, or it depends upon the size of an RU or the number of subcarriers in an RU or the bandwidth of an RU. So the power depends upon the RU size. But when MCS is changed, the power of the DXMU waveform is not changing. It depends upon the bandwidth. No doubt, as the MCS change, the number of samples is changing, the time duration is changing, but the TX power of the multi-user packet is not changing with MCS. So this is a conclusion. So that's all I have to say in this experiment.